is known as perihelion. So nearby position is called perihelion, whereas this position A, which is far off position, this is called aphelion. So nearby position is perihelion and far off position is aphelion. Then what is this distance? What is the position of this perihelion from the sun? So let's call it as RP. As you can see, so this is A and this is EA. So this RP would be A minus EA. So this is the position of perihelion. Same way, if you define the distance or the separation of the aphelion point, so this is, we call it as RA, and you can see this is A plus EA and this is aphelion. So any doubt from this part? So good number of students have joined. So very good morning to all of you. I hope you people are understanding this part, whatever we have covered. Anyone, any doubt from this part? Fine. So we have understood the position of the perihelion and aphelion from the sun. So this is law of orbits. All the planets, they revolve around sun in elliptical orbits, and sun being at one of the focus. So this is the equation of ellipse. So this is the only area where you have the usage of this ellipse equation, and E, we have just defined it as eccentricity, the value of E, that is between 0 to 1. Then the nearby position when your planet revolving around the sun is at nearby position, we call this position as perihelion, whereas the position which is a bit far away from the sun, that is called aphelion, and the radius of this perihelion and aphelion, we have just understood it mathematically also. Any doubt from this part? So shall we move? So this is the very first Kepler's law, and we call it as law of orbits. Then what is the next law? That is law of areas. So law of areas. What is this law of areas? It says the line that joins any planet to the sun sweeps out equal areas in equal intervals of time. That means areal velocity remains constant. So this is all a story about the very basic concept, because there is no external torque, so if there is no external torque, so torque is 0, and we know torque is dl by dt. So this is in vector form. So dl by dt. So if external torque is 0, what it means? Angular momentum remains constant. So this is the underlying principle to understand this concept, and it says the areal velocity. The law of area says areal velocity, that means the rate at which you are sweeping out area. So that means delta A by delta T, which is basically defined as L by 2m, where L is the angular momentum and mass, that is m is the mass of the planet. So it means if angular momentum remains constant, so the whole L by 2m remains constant, and that clearly says this aerial velocity remains constant. Now before we move on with this concept, I would like to add one more important concept based on this previous concept again, because we have just understood the angular momentum remains constant. So we know angular momentum L, that remains constant. So let's apply this angular momentum at perihelion and aphelion position. So angular momentum, we know angular momentum is given by mvr, and that remains constant. So at perihelion position, m is mass of the planet, velocity at perihelion position, and rp, that is at perihelion, is equal to mvr, and that is at aphelion position. So this law is very important. Angular momentum remains constant. So we have just applied this, the law of angular momentum, about these two positions, that is perihelion and aphelion position. So what we have understood, if you compare the speed of the particles at perihelion and aphelion positions, so Vp by Va is Ra by Rp. Now if you look at this, what is Ra? That is A plus 1 plus E. So this is Ra, and Rp is A minus Ea, so that means A1 minus E. So this goes. So this 1 plus E by 1 minus E, this ratio defines the ratio of the speed of the planet about, like when it is passing through perihelion and aphelion position. So any doubt from this part? Anything you would like to ask? So Kumaran has asked one question, speed of planet is more at perihelion. So yes, speed at perihelion, you can compare it with this ratio also, and that clearly states that speed is more at perihelion than aphelion. Now what is this Vp? We can write it down as omega r also. So when you extend this, so this is omega p Rp by omega a Ra, and this is Ra by Rp. So when you compare omega p by omega a, so that means it becomes Ra square by Rp square, and Ra, so that gives you 1 plus E, and that gives you 1 minus E. So now we have the ratio of their angular speed also when it is passing through perihelion and aphelion positions. So I think this has made very clear to all of us, when particle or your planet is passing through this position, perihelion, when it is at nearby position, its speed definitely would be more. We can understand it from this ratio very well. Any doubt? So I think Kumaran, you got your answer. Any doubt? Shall we move? Or you would like to ask anything? Fine. So let's move on to the same concept again. So that means law of areas. So we have just stated its aerial velocity remains constant because there is no external torque, and we know external torque, when there is no external torque, angular momentum remains constant, and aerial velocity, that is given by L by 2m. So L being constant, m mass of the planet remains constant, so aerial velocity remains constant. So it means, now coming back to again, so what is this? When your planet is at nearby position, So this is perihelion, and when it is away, so this is your aphelion position. Got it? Now, to keep the aerial velocity constant, a planet has to sweep out more area. It means planet has to move fast when it is at perihelion position, and it sweeps out equal areas in equal intervals of time. So you can see, just to maintain that aerial velocity constant, so here the planet would be comparatively slower as compared to your perihelion position. So any doubt from this part? So yes, when your planet is nearby to sun, when it is at its perihelion position, so the speed would definitely be more as compared to when it is at its aphelion position. Sure? Understood? This we can understand it from one, again, very important principle, because this angular momentum remains constant. So it means IP omega P is equal to IA omega A. So I omega, that also remains constant. So using this principle also, using this law also, we can very well show when your planet is at its perihelion position, definitely it would be fast, and when it is at its aphelion position, it would be slow. So I think this is all for this Kepler's law. Shall we move? Now, the third law. Third law is again very important law, and this is all about your law of periods. So, law of period says the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. So it says time period. So it means time taken by the planet to complete one revolution around sun, that is, so square of the time period is directly proportional to cube of the semi-major axis. So let it be R. So this is the law of periods. So this is law of periods that clearly says square of its time period is directly proportional to cube of semi-major axis. So this time we are keeping it as R. So this is law of periods. And this law has a great application because this law has variety of numericals. So based on that, let's attempt one or two numericals. So then we'll move forward. Yes, the very first numerical based on this Kepler's law, and that is purely again from the law of periods. It says time period of revolution of a satellite around a planet is 6 hours. Fine. If the radius of the orbit of the satellite is increased by 3 times of its previous value, time period, the new time period of revolution will be. So based on this, it says t square is directly proportional to r cube. This is what we have just covered. So t1 square is directly proportional to r1 cube, and t1 is given to you as 6 hours. Fine. We have to find out new time period of revolution when its radius of orbit is increased by 3 times. Increased. So your R2 would be something like, this is R1 plus increased by 3 times. So this is the actual statement. So that means it becomes 4R1 cube. So the new radius of the orbit would be 4 times r1, and simply we'll go with the ratio to solve this. So what is t1? 6 hours. We need to find out t square. So this is r1 cube by 4 r1 cube. So it gives you 64, and when you solve the value of t2, so that would be 6 square into 64 the whole under the root, and 6 square will give you 6, 64 will give you 8, and that gives you 48 hours as the new time period of revolution. So this is a very simple numerical based on this, that is Kepler's law of planetary motion, and that is from the law of this is law of periods. Any doubt? Anything you would like to ask? Am I not audible? I mean, like 1 or 2 students, they are saying no sound, voice not coming. I would request, I mean, like, is there any sound problem to the rest of the students? If it is there, please. I think it is audible. So I request you please check at your end. From our side, this is completely fine. Good. Subrajit Sinha has answered this one. Yes, audible, clearly audible. So there are 2-3 students, Harsh, some Crick Aura, and Purnima Yadav, some Metsnex, whosoever is there. So audio is I mean, like, clearly there. So please check it at your end. Now, any doubt from this part? Shall we? So this is, we are confirming from the answer slide as well, the new time period of revolution for this is 48 hours only. Let's move to the next question. If the ratio of time periods of revolution around the sun is 27:1 for planets A and B, then ratio of distances of 2 planets RB by RA from the sun. So there is spelling error, no doubt. So just ignore this for this part. So now we know T square is directly proportional to R cube. So what is this? TA square by TB square is RA cube by RB cube. And we have to find out RB by RA. So this is RB by RA. So that is TB by TA. So from this part, this T can, or this R can be written as, because we are writing it as, so this is 2 by 3. So this ratio is, because you are given 27:1, but that is for, because what is given to you as TA by TB, and that is 27:1. So but we are taking the reciprocal or the reverse ratio. So this is 2 by 3, and this can be written as 3 square, and this is 2 by 3. This is 3 cube rather, and this gives you 3 square. So this is 1:9. So 1:9, yes, the very first option. Any doubt? So this is again the very fine numerical based on the law of periods again from the Kepler's law. Any doubt from this part? If you have any doubt, you please clear. I would rather suggest you please keep on clearing your doubt from the current session, so that when you end up with this session, you should be at least prepared for one very powerful chapter, that is your gravitation. So no doubt. So shall we move? Fine, thank you. So we have just verified the answer as 1/9 only. Then the next part of this important chapter is universal law of gravitation. And this is Newton's law of gravitation. So this is stated by Newton, verified by Newton experimentally. So it says every particle of the matter, every particle, howsoever small it may be. So every particle of the matter in the universe attracts every other particle with a force which is directly proportional to the product of the masses. So no doubt it clearly says it is directly proportional to product of the masses. So it says you have two masses. So let's keep these two masses as m1 and m2. So they are separated by some distance r. So your statement says every particle of matter in the universe attracts every other particle with a force which is directly proportional to the product of the masses. So we have just put the statement in some mathematical form. Product of the masses of the particles and inversely proportional to the square of the distance. So inversely proportional to square of the distance between them. And when you rearrange and replace this proportionality sign with capital G, so your force becomes F is equal to capital G m1 m2 by r square, where this capital G is your gravitational constant, and its value is 6.67 into 10 raised to the power minus 11. And in SI system, units are Newton meter square by kg square. So this is the simplest form of Newton's law of gravitation, which has stated that every particle of the universe, howsoever small it may be, so that particle attracts every other particle with a force which is directly proportional to product of the masses and inversely to the square of the separation between them. And this is the mathematical form for the Newton's law. Any doubt? So let's highlight few important characteristics of this force also. So as you can see, the very first property of this is directly proportional to product of the masses. It's following the inverse square law. So it means with the increase in separation, this force keeps on decreasing, and this is your, what is this? Inverse square function. So what kind of shape you are representing through this graph? Yes, this is hyperbolic shape. Got it? So this is gravitational force is the weakest force of the nature. So this is one of the fundamental forces, but among all the basic fundamental forces. So we have 4 types of fundamental forces, and this gravitational force is the weakest among all the 4 forces. And this is a conservative force. So this is conservative in nature. And I think we did cover this part, conservative force, in our last YouTube series, and that was conducted almost 15-20 days back. So that was about work by energy. So we did discuss this conservative force. So you can refer to that session that is available still there on the YouTube. So you can access that video lecture. So this is a conservative force. This is a central force. And then there is one interactive particle. So that interactive particle between these two masses. So it is always proposed that whenever these two particles, they are interacting, so they are exchanging some energy, so they are exchanging some hypothetical particle, and that exchange particle for this gravitational force is basically your graviton. So graviton is that proposed hypothetical particle that is getting exchanged between these two masses whenever they are interacting. So these are the few basic characteristics of your this basic force, that is force of gravitation. So any doubt from this part? Anything? So Pankaj, you got late, you joined very late. So any doubt from this part? Fine. So shall we attempt one basic numerical based on this? Shall we? Okay, fine. Let's suppose I'm giving you a very fine numerical that is based on some important concept. So it says divide mass m into 2 parts such that these 2 parts, they experience maximum force of attraction. So this is again one of the fundamental numerical we have based on this, and it is very fine numerical. So what is given to us is a mass m. So we have to divide this mass into 2 parts such that the 2 parts you are getting, they should have maximum force of attraction. So let's do it like so let's suppose one part we break it into small m, the other left out part would definitely be m minus m, and they are placed at separation r. So as per your law, the force between them is given by m1 m2 by r square. So this is the one. Now this force, if you look at this, is basically function of this mass is fixed. This is a known mass. This is a constant value. So this force is a function of small m only, and the force is defined as the maximum force. And for the force to be maximum, we need to define dF by dm, and that has to be equal to 0. This is the first condition. But is this the only condition for the force to be maximum, or do we need to check? We need to check its second order derivative also. And for the force to be maximum, this has to be greater than or equal to 0, or what is this? So let's check what we are getting it as. So if you define dF by dm first, so this g being constant, r being constant, will not participate in the derivative part. So this is basically d by dm of capital M into small m minus m square. Got it? And when you define it, so it's m minus 2m, and for the force to be maximum, we just put it as 0, and this m becomes, small m becomes this one. And I did mention the second order derivative, and second order derivative for this part is equal to minus 2. And what is this? Less than 0. And that is the important condition to check. Yes, second order derivative is this one, so definitely force would be maximum. So Hardik has given a right option. Hardik, it is capital M by 2, because we are looking for small m, so it is capital M by 2, right? So any doubt from this part? So we got the force, and that force is maximum between these two particles. So shall we move to the next? Any doubt? Any doubt from this part? I'm again suggesting you, if you have any doubt from the current session, please keep on clearing your doubts, keep on asking, so that by the end of this session, you would be able to solve varieties of numericals from the gravitation part. So this is our ultimate goal, to help you. So now let's move to the next topic, next numerical, based on the same, rather this is based on the Newton's law of gravitation. It says, if the masses of two spherical bodies, so if the masses of the two spherical bodies are quadrupled, and the distance between their centers is doubled, then percentage increase in the force of gravitation between them. So let's suppose we have two masses. So these two masses are m1, m2, and they are separated by this r. So initially your force is G m1 m2 by r square. So this is the formula. Now question says, if masses are quadrupled. So what do you mean by quadrupled? Quadrupled, so the new force, I am labeling it as F prime. So this is G, masses are quadrupled, means these masses are 4 times. And the centers is doubled. So their separation is doubled. So this becomes 2r whole square. So that makes as 4r square. So we have to find out percentage increase in the force. So just I would rather suggest you go for the ratio, and when you take the ratio, you can clearly see this F dash is 4 times F. But we have to find out the percentage increase. So percentage increase in force is F dash minus F by F into 100. So that makes it 300%. And this is how we'll have the answer. So this is basically a numerical based on your Newton's law of gravitation. Good, Hardik. So you are very active. Keep it up. Well done. It's 300%. I think now, I mean, like people are getting involved with the calculations also, and that is a good sign. When you attend a session, when you attend a particular live class, so I would rather suggest you sit with your paper, pencil, or whatever registers you maintain. Keep on noting it down, keep on recording the important points, keep on, though you can have the access of all these video lectures even after the session also, even after the live class, but still I would rather suggest you, the moment you are participating, the moment you are interacting, start learning from that moment only. So this is all about for this part. Anything you would like to confirm from this section, or shall we move? So this is 300%. Now the next part is acceleration due to gravity. So acceleration due to gravity is what? It's small g. And acceleration due to gravity is basically gm by r square. So here we are talking about m as mass of earth. So g being gravitational constant 6.67 10 to the power minus 11 in SI system, mass of earth is 6 into 10 to the power 24 kg. So all these values are in standard SI system. So this is Newton meter square per kg square, and this radius of earth is 6400 kilometers, which we can write it down as 6.4 into 10 to the power 6 meters. And when you took, or when you put all these values in this expression, that will give you the precise value of acceleration due to gravity as 9.8 meter per second square. So whenever you allow a body to fall under the effect of gravity on surface of earth, whatever acceleration body will acquire, that is called acceleration due to gravity, and this is 9.8 meter per second square very precisely for earth. Got it? Any doubt from this part? So this is acceleration due to gravity, capital G, capital M by r square. So I think this is clear to everyone. There is no doubt about that. So this is acceleration due to gravity. Now, if you assume Earth to be a sphere of uniform density. So if you assume your Earth to be a sphere of uniform density, then mass of Earth can also be written as its volume into density. So this density D is assumed to be uniform throughout. It is an assumption, assumed to be. Got it? So when you put the value of this mass there, so this acceleration due to gravity becomes 4 by 3 pi g r into d. Whereas this part is constant almost for all, and primarily it varies on these two parameters, that is your size, that is radius, and its assumed constant density. So there is another formula for acceleration due to gravity in terms of density and size, that is radius of Earth. So any doubt from this part? These all are very standardized values, so I would rather suggest you for this mass of Earth, radius of Earth, these all are very standardized values. You may not find all these values in any of the numerical, so I would rather suggest you please learn it, you practice it, just put it in writing 2, 3, 4 times and you will retain it forever. That is all for this part. So any doubt? So shall we move with numerical now? Yes. So the next numerical is based on this acceleration due to gravity. It says the density of a planet. So what it says density of a planet is twice that of Earth and radius is also twice as that of Earth. The acceleration due to gravity on the surface of the planet is, and you have to get the answer in terms of GE, which is acceleration due to gravity on surface of Earth. So we have just experienced the value of G as 4 by 3 pi G R into density. So this is what we have just obtained as the expression. So this being constant or universally same for all, so will not participate in this numerical rather. So for Earth, I am putting it as GE, and they are also referring GE as acceleration due to gravity on surface of Earth. So this is radius of Earth and density of Earth. For planet P, let's refer this planet P. So its value for planet P is stated or written as GP, that is acceleration due to gravity on the surface of a planet. The size or the density. So density is twice. So this is the density for the planet, which is twice the density of Earth, and radius is also twice that of Earth. So that means 2 times RE. So that means 4 times RE dE, which is G. So acceleration due to gravity on the surface of planet is 4 times acceleration due to gravity on the surface of Earth. So that means it is 4 times GE. It can be asked like, what is the percentage change? Percentage change in G is 300% again, because this is 4 GE minus GE by G into 100. So that would give you 300% more as compared to acceleration due to gravity on the surface of Earth. So this is, we are talking about planet. Any doubt from this part? So Subrajit Sinha has given me the right option, 4 GE. Very good, Subrajit. Hardik has given me 300%. Good, keep it up. Well, participating well in the class. Good. Any doubt? I think this kind of involvement of the student exactly keeps motivating the teacher for the next part of the session, and that is quite interesting. So we have just verified the answer as 4 times GE. Now acceleration due to gravity above the surface of Earth. So this is again very important. Now just pay attention. So this is your Earth and bodies on this surface. So we have just stated on the surface this G is capital G capital M by R square. Now you take the body to a height h, and here acceleration due to gravity, I am stating it as G prime, G dash, G prime. And now if you look at this, the complete separation of this mass and this center of Earth is R plus H. So that becomes Gm upon R plus H whole square. Got it? And when you take the ratio of these two, so that g dash would be g times r square upon r plus h whole square. We are just taking the ratio of these two. Nothing more, nothing less. Got it? Now this expression when to be used, और हम इस expression का इस्तेमाल कब करते हैं? When your h is comparable to r. But if h is very, very small as compared to r, then this same expression will get reduced to this expression. So this is the characteristics, or this is the difference. You have to note it down very particularly. So now you have two expressions, two values. One is when g and h are comparable. Sorry, when r and h, small h, that height is comparable, then we have to use this expression. And when h, the height is very, very small as compared to radius, then we have to go for the second expression. Any doubt from this part? Any doubt? So let's attempt one numerical. It says, yes, I would like to highlight, this is value of g dash. So when you multiply both sides by this, so primarily this is the first expression. I am just writing down the first expression, and your weight becomes, at a height becomes this one. So the next numerical is based on this concept only. A body weighs 200 Newton on the surface of Earth. How much will it weigh at a height h equal to re by 4? Very important point to be noted, h equal to re by 4. So this is almost 25%, and this is h is comparable to r. It's not a small which can be neglected as compared to the size of Earth. So it means we have to go for the second expression, and this expression clearly says mg r square upon r plus h whole square. So very important point to be noted here again. I'm highlighting this point. When your height is comparable to size, that is radius of Earth, and that is comparable in the sense when it is very, very small, I mean like less than 5-7% maximum, then we can go with the other formula. But if it is more than 10% or more than that, here in this case it is almost 25% exactly. So we'll use this formula. So this is mg dash, we need to find out this, and this mg on the surface of Earth, its weight is 200 Newton. This is r square, and this is what? R plus h, where h is r by 4. So when you solve this, so this is r square, and this becomes 5r by 4, and when you square it, it becomes 16 by, this is what? 4 plus 1, 5, and that makes it, so this goes, so this is 8 and 16, 8 is 128 Newton. So that is the answer for this. Any doubt from this part? Shall we move? So there is one student named, hi, I'm well, I'm fine. So Please pay attention. So any doubt from this part? Any doubt? Hardik has given me the right option. Right answer 128. Good, Hardik, keep it up. I'm really impressed. So it's 128 Newton. Now next, let's move to acceleration due to gravity below the surface of Earth. This is below. Now, so this is Earth and you have on the surface, so this G. Again, I continue with my assumption that your Earth is a sphere of uniform density, and in that situation this G is given by this formula. So that means 4 by 3 G R times D. This D is density. So I think if I make a small change for this density, now this time I am using a symbol density as rho. Why? Because my next step would definitely clear this point. Let's suppose you move at a point D below the surface. It means you are going inside the Earth, and that is basically depth. So I am mentioning this depth as D, and this depth is from the surface. So I am going inside from the surface. So here your radius would be, what you are left with is R minus D. And when you find out your G dash, so that means 4 by 3 pi capital G R minus D, and density is still assumed to be same. And in that situation, G, that is G dash at depth, is given by 1 minus D by R. So this is important when you go deep inside the Earth, and that depth which I am taking it as D now, that is defined from the surface. So that means 1 minus D by R. So when you are going inside, and G at the center of Earth, so it means depth becomes R, your G at the center of Earth would be 0. So it means if you understand the graph like this, so G at the center of Earth is 0, so that keeps on increasing. On the surface it is there, and outside the surface it follows inverse square law. So this is how G varies with respect to your R, and this is at center. Any doubt from this part? Any doubt? So this is how G dash, that is with the depth, how it varies with the depth. So G dash is equal to G 1 minus D by R. Now if I ask you to find out a relation between depth D and height h for same value of G, and that height is again very small as compared to the size. So this is my assumption. So it says G at height is equal to G at depth, and for small this is given to you as 1 minus 2h by R, and this is G 1 minus D by R. And when you just look at this, so this is what? 2h is equal to D. So this is important. It means for 2 times the height, sorry, this is 2h equal to d. So this is depth. So 2h equal to d. It means 2 times the height is equal to the depth. So if you are going d inside, you have the same value of g as you are going 2 times the height. So value of g would remain same at these 2 positions. So this is very important, and this shortcut can be used for varieties of numericals if they ask you the relation for the same value of g, that is the relation between height and depth. Any doubt? So there is one student called Sharma Boy who has given me the right answer, d is equal to 2h. That's good. Good, keep it up. Now, so we have a numerical based on the same, and it says at what depth from the surface of Earth acceleration due to gravity will be 1/2 of the value of g on the surface of Earth. So g at depth is given by g dash equal to g1 minus d by r, and it says it becomes 1/2 of the value of the g on the surface of Earth. So this goes, so that gives me value of b as r by 2 as the answer. So all these areas are very interesting. All these questions are very close to your formats. What you need to understand is you just need to practice few more numericals based on the same concept, so that will keep adding to your performance, and that will definitely help you to understand or will help you to score well. Shall we move? Any doubt? So Hardik has given me the right answer. Good, Hardik, keep it up. Well done. And Mr. Sharma also has given me the right answer. Good, Sharma. Now we have the concept of gravitational potential energy. So this is again quite interesting. Gravitational potential energy is defined as amount of work done in bringing a body from infinity to a given point under the influence of other body. So if you understand it a bit, so this is, let's suppose, Earth and its mass is m. So let's suppose this is a small body m, may be defined at position A, and let's keep it at position x. So what is the force between these two masses, small m and this? And this force is g m m by x square. You got it or not? Now you take this to another point, maybe B. So you are taking it, so external force is there, force of gravity is there, that is downward. So you are taking the body against the force of gravity with the help of some external force. So if you are finding it as work done by gravitational force, so we are taking it by small values. So let's suppose that small work done is f dx. So if we are finding the work done by this gravitational force, so this is against, so this is cos 180 degree, and for the total we need to integrate it. Got it? So that gives you minus, and this is g m m by x square into dx, and that gives you, this is capital G capital M, and when you do the integration of this part, so that gives you minus 1 by x. So this minus minus will give you plus, and this is the value, maybe from position 1 to position 2, whatever it is. So position A to position B, and it is this work done against this gravitational force, that is basically stored as potential energy. And when you define this work done, so this is GMM by RB minus GMM by RA. Got it? And when you take it from surface, so it means from the surface where your separation is R to a position at infinity. So this is, so 1 by infinity becomes 0, so this is minus GMM by R. So this is when you are taking it from surface to infinity, or if I do it the other way, because this is a conservative force, if you define it from infinity to the surface, this potential energy of the body remains same. And you know, in the whole story, potential energy is assumed to be 0 or taken as 0 at infinity. So this is the concept of gravitational potential energy. Any doubt from this part? Shall we? Now, energy required to raise a body of mass m from Earth's surface to a height of r, where r is radius of Earth. We know gravitational potential energy minus g m m by its position or the separation or its orbital radius. You say it like that. So what is the initial potential energy? So initial potential energy is when body is at the surface. So it means this r is definitely, this r is taken as the size of the Earth when body is situated at the surface of Earth. So this is the initial potential energy of the mass m. Any doubt from this part? Initial potential energy when body is situated at point or on the surface. Then final potential energy to a height of r, height. So if you replace it with this formula, it would be rather more logical, because you can see this is a generalized version for orbital radius. Here we are talking about the radius of Earth plus height. So in the very first situation when body was at surface, so this h was 0, so we got this initial. But for the final one, this height is equal to r only, and this is GMM by r plus r becomes 2r, and the energy required is final minus initial. You got it or not? And this is minus GMM by 2r, and this minus and this minus will make it plus, and that would give you GMM by 2r. And using this expression, capital G, capital M, because we know G is equal to capital G, capital M by r square. So if you look at this, capital G, capital M as G r square. So G r square M by 2 times r. So this r goes. So this is mgr by 2. So this is mgr by 2. So definitely we'll go with the first option. So this is the concept of gravitational potential energy, and we have a very simplest and the beautiful numerical based on the same concept. Any doubt you have? Nilesh, sir, nahi samajh aaya. So where is the problem Nilesh. So this is the initial potential energy. Have you understood the concept of potential energy? If you have understood the potential energy, then only you can solve the numerical. So this is the initial potential energy of the body when it is placed at the surface of Earth, and this is the final potential energy when it is taken to a height r. And the difference in the potential energy, final minus initial, will give you the amount of energy that is required for this change. That is sort of amount of work done. I hope if you follow the lecture from, the basic, like what we did last 10 minutes back only, that would help you. So Raj Gupta, yes, any doubt? Nilesh? Total energy, Raj Gupta, this is basically the body is at rest, so kinetic energy is definitely at rest because we are just taking the body at rest to a level. तो हम एक body को एक height से उठाकर दूसरी height पर लेकर जा रहे हैं. Had it been a case of satellite motion where the body has some kinetic energy also, then definitely. Got it? So will not go with the total energy because this is the concept of total energy, like kinetic energy is not there because body is at rest, stationary. So we are talking about potential energy. Body is not in motion. So there is no other kinetic energy involved. So let's move to, I hope you have understood it, Raj. Shall we? So this is the concept. Any doubt? Okay, fine. Thank you, Raj. Now we have three particles of masses m, 2m, 2m are placed at the corners of an equilateral triangle of side x. Calculate potential energy of the system. Now, for this kind of numerical, just pay attention. So first I would like to explain, I would like to highlight a generalized version for gravitational potential energy for a configuration, for a system of particles. You know how potential energy was defined? Potential energy was, or potential energy is defined as energy possessed by a body by virtue of its position or by virtue of its configuration. So here we are talking about configuration. So let's suppose we have three masses. This is a generalized version. So we are talking about potential energy for a configuration. So we have a general separation R12. Sorry, this is, let it be 3. So this is R13 and this separation is R23. So when you are asked to find out potential energy for the system, so what is this? So how many pairs? This is one pair, this is another pair, and this is another pair. So potential energy for all the three pairs would finally be added to define the potential energy of the system. So this is very simple now. So this is minus G m1 m2 by R12. For the second pair, minus G m2 m3 by R23, and this is minus G m1 m3 by R13. So this configuration will have potential energy given by this format or this expression. So I hope now we are clear on gravitational potential energy for a configuration. Got it? Now let's come to the question. So we have three particles m, 2m, 2m. So this is the same configuration we have placed at the corners. So this is m, 2m, 2m, and all sides are same. Any doubt? So let's use the same format, same numerical. So very first, so we need to find out potential energy of the system. So very first pair for this is minus g m into 2m by x. So that is the first pair we have. Second pair minus g m again 2m by x, and the third pair is minus g 2m. So I am talking about this pair 2m by x. So it's simply when you add up all. Can you pick up the option? I'm leaving it to you. If you can pick up the option by using this formula, so please help me to get the answer for this configuration. It's quite easy now. So this 2, and this 4 will make it what? 8. So that is the option we have. Any doubt? Good. So Raj, you are doing good. Keep it up. Any doubt? So let's verify the answer from the slide also. Yes, this is the same. Gravitational potential. So gravitational potential is V, and gravitational potential due to gravitational force of the earth is defined as potential energy of a particle of unit mass at that point. So what was the gravitational potential energy? So that was minus g capital M small m by, let's suppose general formula is small r. So that says potential energy per unit mass. So it means that is minus g capital M by r. So that is the formula for the gravitational potential, and this is definitely a scalar quantity. Got it or not? So based on that, if I give you a very simple numerical of the same configuration, let's suppose this is mass m, this is mass m, this is mass m, and this is again an equilateral configuration. If I ask you to find out gravitational potential at the centroid, so we have to find out gravitational potential at the centroid for this configuration. So purely this is, if this is side x, so this distance is x by root 3. For this one mass, so this is minus g m by x by root 3. For the second mass, this is also same. For the third mass also it is same. So we simply put a numerical number 3 out there, and that would define the gravitational potential at the centroid for this configuration. Got it? Now we have another article that is called escape speed. So what do you mean by escape speed? So let's suppose this is your earth and body is at this position. So this is mass small m and this is m. Now we have to project this body with some speed. So it means we have to give some kinetic energy so that it just escapes. So let's suppose this is the gravitational field region for this earth. So the moment you project it, it just ends up there. So it just overcomes the gravitational pull and manages to reach at a point which is just outside the boundary of your field region. So in this situation, So Raj in this situation will go with the conservation of energy. So I'm talking about conservation of mechanical energy. So what is the total energy initially that should match with the total energy at the final point? So at this point we have gravitational potential energy on the surface, and that is minus gmm by r. So this is the gravitational potential energy, plus we project it with some speed, we call it as escape speed, so that it just manages to reach here. So when you say manages to reach here, so it comes to rest, so final kinetic energy would definitely be 0, because this is outside the field region and assumed to be the 0 potential energy state. So this is 0, and when you solve it, so this is the escape speed, that is the minimum speed with which body is projected up so that it manages to just reach the outer surface of this gravitational field part. So this is the escape speed. Now again, if you put the value of capital G, capital M as g r square, so the same formula will get reduced to this one. And if you put the value of mass again as 4 by 3 pi r cube into density rho, so this is another formula for the escape speed. So now, depending on the data given, depending on the numerical values given, we may be asked to find out escape speed for, for any surface from any of the planet. So depending on the data given, we may use this formula, the second formula, or may we go with the third formula also. So any doubt from this part? Yes. This is Srijan and Raj Gupta. They have given me the option also, and from the surface of Earth, where you put all the numerical values for all these constants. So that means 11.2 kilometer per second, and that is the escape speed from the planet Earth, from the surface Earth. And you know, this escape speed is independent of the orientation, the way. It means if you project your body maybe at some angle theta, the escape speed would remain same, because this is independent of the inclination, independent of this angle of projection. So that would go same for all these. So this is the concept of escape speed. Any doubt? So yes, there is one question. This escape speed is independent of the mass. It means if you throw an object, maybe a small body, maybe a large body, or maybe a very heavy large body, so escape speed would remain same for all three, because that is independent of the mass of the object. That is also very important. So good participation from all these viewers. Good bacho, keep it up. So I think now let's attempt one numerical based on this. The ratio of escape velocity at Earth to the escape velocity at a planet whose radius is half and mean density is 4 times. So it means you are talking about escape speed as, so which formula? 2g by r, and for the mass this is 4 by 3 I r cube into density. So this is basically directly proportional to, so this becomes r square, and when you take r square from the square root, so this is directly proportional to like this. So for Earth, so this is Re density of Earth under the root, and for the planet, so whose radius is half, means RE by 2, and density is 4 times that of Earth. So when you take this, so this goes with this, and this ratio comes out to be 1:1. Yes, very fine. Any doubt from this part? Any doubt? Not option 44. What do you mean by 44? Good. So Raj has given me the right answer. Sanjana has given me the right answer. Good. Keep it up. Well done, students. Well done. So you are gaining actually. Good. It's a good sign. So it's 1:1. Then we have satellite. So this is again important. Earth satellite. So what do you mean by satellite? Any heavenly body that keeps revolving around a given mass in well-defined orbit, that is called satellite. Got it or not? So this is your Earth. Mass is m, radius is r. So this is r. So we have at height h, so we have a satellite of mass m. So that is around this planet Earth. So otherwise, what is your natural satellite for Earth? Keep guessing and give me the answer in the comment section. So is there any gravitational force between this satellite of mass small m and the Earth? Yes, so this is the gravitational force. As you can see, this satellite of mass m is orbiting in this circular orbit. So this gravitational force definitely will provide you centripetal force to your satellite. And from here, you will have the value of orbital speed, because here we are talking about the orbital speed. So this orbital speed becomes gm upon r plus h under the root. If this is very close to Earth, then definitely r plus h is roughly equal to this r only, and your orbital speed becomes gm by r under the root. Whereas in the last section we had 2gm by r as your orbital speed. So this is root 2 times orbital speed. You got it or not? Now if I ask you a very fine question, find percentage increase in speed for this satellite so as to escape. So if I have to increase the speed of this satellite in this orbit so that it just escapes, so that percentage increases, it means I have to reach my escape speed, whereas I am having orbital speed. So this is root 2 times orbital speed. And when you solve it, it gives you 41.4%. So if you increase the speed of this satellite, which is orbiting in this orbit, so if you increase the value of its speed by just 41.4%, it would definitely escape. Got it? So this is one important area, and based on this, there is, so before I think I need to calculate the energy also. So if I calculate the energy of satellite, this is important. So what is the potential energy? So potential energy is minus Gmm by R plus H. Can you see this? And this is -1, because this satellite is in motion with some orbital speed. So its kinetic energy is half m v naught square, and from this part if I extract the value of this one, so that gives me Gmm upon 2 times R plus H. What is the total energy? So total energy is potential plus kinetic, and that gives me minus Gmm upon 2 times R plus H. So we have 3 important relations. These are very, very important. Now this time, Raj, we have to make use of total energy. So that total energy is minus capital G capital M small m by 2 R plus H. So based on this, we have very fine numerical. A satellite of mass is orbiting the Earth. Yes, this is orbiting. It means now you have a concept of kinetic energy. So it is at an altitude also, so it has some potential energy also. So in this situation, we'll definitely talk about conservation of energy. So satellite of mass m is orbiting at an altitude of this. So what is the total energy of the satellite initially? So just look at the expression minus Gmm upon 2 R plus H. And this time this R is, this H is rather R by 2. So R plus R by 2 becomes 3R by 2. So this is the total energy of the satellite, total energy. To increase its altitude to 2R. So now we have to increase its altitude to 2R. So final energy, again, the total energy that is in final state is minus Gmm upon 2 times R plus H. So R plus 2R becomes 3R. And we have to find out extra energy. So that extra energy is total energy final minus total energy initial. So this is minus Gmm by 6R, and this minus will become, so this is 3R. So this becomes plus, and when you solve it, it becomes 6R. So this is 2, this is minus Gmm plus 2 Gmm. So that gives you Gmm by 6R. And for this Gmm, capital G, capital M, again we'll put capital GR square, sorry, small gr square. So this becomes mgr by 6. So this is the required answer for this mgr by 6. So let's verify the answer. Yes, so this is mgr by 6. So this is all from my side and myself, your physics faculty at Aakash, Puneet Kathuria. So any doubt, anything else you would like to ask, please keep on commenting, please keep on watching this video so that it should help all the others NEET aspirants for the rest of their preparation. Thank you very much. Thank you, kids.